Now we can see how these ideas relate to electric fields. There are a few important differences between electric fields and gravitational fields. Firstly, with electric fields, we have both positive and negative charges. And it's those charges that are causing the forces of repulsion and attraction. The fact that we have negative charges and positive charges does mean that we can now have both attractive and repulsive forces between charges. The second difference is that with gravity, two positive masses attract. With electric fields, two positive charges repel. If you want a force of attraction with electric charges, you need a positive charge and a negative charge. They will attract. But two like charges, two positive charges or two negative charges, will repel. This is encapsulated in the formula known as Coulomb's law. F, the force of attraction between two charges, is 1 over 4 pi epsilon naught times the product of the two charges divided by r squared. Once again, it's an inverse square law. But this is a repulsive force. If Q1 and Q2 are both positive, or Q1 and Q2 are both negative, then this would evaluate to be a positive number, and this force would be repulsive. If Q1 and Q2 are different, however, if one is positive and one is negative, then this would all evaluate to a negative number, and that would indicate a force of attraction. The other difference is that the constant of proportionality, which was a simple big G for gravity, is now 1 over 4 pi epsilon naught. Why 1 over 4 pi? Well, it makes the application of something called Gauss's law much easier. But that will have to wait until the next one of these little talks. You can define an electric potential as well. The electric potential is the amount of energy required to move a unit charge from infinity to a point, a distance r away from any particular charge, let's say Q1. The amount of work required to get a unit charge from there to there is 1 over 4 pi epsilon naught Q1 over r. You can get that from integrating the force over the distance that it's moved, in a similar way as we did for gravity earlier. I won't go through the calculation again. This is the answer you get this time. It's the electrical potential. Sometimes call that V. And this is the amount of energy required to get a unit charge from infinity away to a point r away from Q1. And using potentials makes it easier to calculate the energy required to move charges around circuits than doing all the integration all the time, which is the main reason that use of potential is so popular. We can use the concept of flux for electrical fields as well, because the field strength is proportional to 1 over r squared. It's an inverse square law, so we can use the concept of flux. Now, the flux density is equal to the field strength. And the field strength is the force on a unit, in this case, a unit charge. And the force on the unit charge we can get from Coulomb's law here, 1 over 4 pi epsilon naught Q1 over r squared. And Q2 is just equal to 1 because it's the force on a unit charge that I'm concerned with here. Well, if that's the flux density, then I could work out the total amount of flux emerging from a charge of Q1. Because I would just have to multiply the flux density by the surface area of a sphere. If the sphere is a distance r away from Q1, so that's the radius of this sphere, then the surface area of this sphere is 4 pi r squared. So the total flux emerging from a charge of Q1 is just the flux density multiplied by the total surface area that the flux is emerging out of, 4 pi r squared. The 4 pi's cancel, the r squareds cancel, it's just Q1 over epsilon naught. The total flux emerging from a charge of Q1 is Q1 over epsilon naught. The 4 pi's have cancelled, and in fact this was the reason that people put the 4 pi into Coulomb's law in the first place, because they found that flux was such a useful concept that having a simple law like the total flux emerging from a charge is equal to the charge divided by a constant, in this case constant epsilon naught, that was an easy thing to remember and an easy thing to work with. You can gain an appreciation of what's going on by playing around with the demo as well, and I would suggest you do this. You can add positive charges with the button here, and you'll see at the moment by default it shows the field strength in terms of the arrows, but we can show flux just by checking this checkbox here, and these are the flux lines. They emerge from positive charges. Remember that flux lines are just a visual representation of this concept of flux, and flux is like light emerging from positive charges. The direction of the flux is in the direction that a unit charge would move. So, if you're some distance from a positive charge like this, a unit positive charge, all unit charges are by definition positive charges, would be repelled by this positive charge here, so would be experiencing a force away from this charge, so the direction of the flux is away from this charge. As we've seen before, flux lines cannot start or stop in free space, so they would start here at the positive charge and head off to infinity. And it's just a way of representing this completely uniform stream of flux emerging from this positive charge. If I put a negative charge on the screen as well, all the flux lines disappear. And that's because the negative charge and the positive charge are now in exactly the same place and are cancelling each other out. So there is no net flux emerging from anywhere because the field strength everywhere is zero. The negative charge would be attracting a unit charge, and the positive charge in the middle would be repelling a unit charge with exactly the same strength of force. So those two forces would cancel out perfectly, and a unit charge would not experience any net force anywhere. So the flux density is zero, which means there would be no flux lines at all. If I move the negative charge slightly away, though, you suddenly see all of the flux lines emerging, and you'll see that flux lines emerge from positive charges, and they end up on negative charges. And this is where the analogy of light with flux breaks down a little bit. Positive charges you can think of like light bulbs. They shine flux out in all different directions. Negative charges are more like black holes. They suck light into them. So the flux lines, which show the direction in which all of this conceptual flux is travelling, emerge from the positive charge and end up on the negative charge, or head off to infinity. If there are two positive charges, then you'll see that the flux lines sort of repel each other. I noticed this when I was playing around with this demo, and you can limit the length of the flux lines in the demo. Now, real flux lines are not limited in length. Real flux lines travel from positive charges and they end up on negative charges, or they go off to infinity. But if you just draw the flux lines so that they stop some distance away from the charges like this, you can sort of get a visual appreciation of the fact that these two positive charges just don't like each other and try to push each other away. Whereas if I add a negative charge, then the negative charge is kind of welcomed by the positive charge. And that's the force of attraction in visual form between the negative charge and the positive charges. But of course, in real life, flux lines do not start in the middle of space. They do this, and you get these rather strange patterns of flux lines when you have multiple positive and negative charges around. I've also added this feature that you can animate the flux, so you can sort of see the direction in which the flux is moving. It leaves positive charges and heads out, and it goes to negative charges. I also wanted to try and illustrate that it's not true that flux only travels along flux lines. This is just a way of drawing it. Flux is emerging in all possible directions from these positive charges. And I thought I could perhaps show that by allowing the directions in which the flux lines that I've drawn coming out of the positive charges to vary. And if you do that, you get this kind of thing. And I'm not sure that's terribly helpful. It's quite entertaining to look at, but it's getting a bit confusing. I think maybe just that might be the best way to think about things. And if you've got the animation, you don't really need the arrows either. You can see the flux is emerging from the positive charges and collapsing into the negative charges. Okay, that's all I wanted to say this time. Next time, we'll be looking at applying these concepts of flux to situations where there isn't just one charge, there are two. The problem of the dipole.